Hey, Mr. Rainsberg here, and I'm going to be starting you off in Chapter 8, which is Estimating with Confidence. And in this lesson, we're looking at 8.1, which is the basics of confidence intervals. And we're going to be discussing these 5 different learning objectives for today. And the first 2 are interpreting a confidence level versus interpreting a confidence interval. 2 separate things, and making sure we can do them in context. Describing how a confidence interval gives a range of plausible, and I like the word plausible because that's not the word possible, it's the word plausible. Interesting. I'm describing the inference conditions. So again, we've discussed conditions in previous videos for this, and then explaining practical issues that can affect the interpretation of a confidence level. So let's go ahead and get started. We can see here that this is our inference decision tree, and you can see I drew the dashed line to show where we were in Chapter 7, which was focusing on can we distinguish between a mean versus a proportion. So when we're given a population parameter, can we determine, are we given a mu, so that way we're dealing with x bar, or are we dealing with our proportion, p? And so we start collecting samples for p hat. And now we're going to the right side of that dashed line. We are looking at different situations involving means and proportions. And notice means has 2 situations. Your sigma is known or your sigma is unknown. And what that means is your population standard deviation is known to you. It's told to you in the prompt, or it's not told to you in the prompt. It's unknown. We don't know the population standard deviation. So that's a branch that we're going to be going off on in these 8 through 10 chapters here. The other is if you have a proportion. Right now, we're just looking at one sample, and we're going to be dealing with those. So this decision tree, now what's happening is we are going to start seeing us going across and figuring out the rest of these. So Chapter 7 kind of stopped here. Chapters 8, 9, and 10, we now go to the right. So let's begin. Here are some things to keep in mind with Chapter 8 in the beginning. And one of them is our goal in many statistical settings is to take a sample statistic, our x bar or our p hat, and estimate a population parameter. And one of the key things was that in Chapter 4, in order for us to do that, in order for us to generalize our results into a population of interest, to infer our results on that, we need random selection. And that was a big thing in Chapter 4. And so maybe when we're discussing our conditions, maybe one of the conditions deals with being randomly selected. In Chapter 7, we learned that different samples, they yield different results for our estimate. And that was sampling variability. So remember, when you increase your sample size, you decrease your sampling variability. If you decrease your sample size, you increase your variability. And statistical inferences uses this language of probability to express the strength of our conclusions. And remember, we had our ideas of independence and normality in there for Chapter 7 as well. A couple other things to keep in mind with our conditions. And lastly, in this chapter, we're going to learn one method of statistical inference, and that's called confidence intervals. So in other words, we may estimate the value of a parameter that we don't know. We don't know the parameter from a sample statistic. So as we do so, we'll learn not only how to construct a confidence interval, but also how to report probabilities that would describe what would happen if we use this inference method many times. Now, I really like this last one. I think there's a lot of writing there and a lot of hidden descriptions and hidden concepts that may help us later on. We don't know the parameter of interest. And even then, how to construct a confidence interval. So we can report probabilities that would describe what would happen if we did this many times. So there's certain phrases there. Hopefully, as we go through this chapter, this lesson, you will understand how these are used. So let's continue on with the basics. If you had to give one number to estimate an unknown population parameter, what would it be? And this was something we discussed in Chapter 7, an unbiased estimator, and we call these point estimates. If I'm trying to estimate a population mean, well, I'm going to use a sample mean. If I'm trying to estimate a population proportion, p, I'm going to use p hat. So if I'm trying to estimate mu, the population mean, I better use a sample mean. If I'm trying to estimate population proportion p, I better use p hat, the sample proportion. And in these cases, you are providing a point estimate. A point estimator is a statistic that provides an estimate of a population parameter. The value of that statistic for a sample is called a point estimate. It's our best guess. That's for an unknown parameter. It's the best guess we can do. If I don't know my population mean, but I collected a sample and I found the mean of that, that's my point estimate. And what happens if I do that many times? Well, we looked at that with Chapter 7 with sampling distributions. So we learned in Chapter 7 that an ideal point estimator, it will have no bias and it will have low variability. So an ideal point estimator will have no bias and low variability. So since variability is almost always present when we are calculating statistics, it's almost always there from different samples, we have to extend our thinking about estimating parameters to include acknowledging that repeated samples could yield different results. I love that. Repeated samples could yield different results. And again, think about sampling distributions. When we had all of our different sampling distributions, when we collect a sample of 25 and we would find the mean, we would have an X bar and we would plot it on the distribution. But when I collected another one, that was a different X bar, and maybe it went over here. Maybe it went over here. And what happens is they were different. And that's what that's telling us, is we have to acknowledge that repeated samples yield different results. So let's try it out in this problem. Our point estimate is our best guess of an unknown parameter. Let's say it with me. A point estimate is our best guess at the unknown parameter. So here we have three different settings, and we're asked to determine the point estimator we would use to calculate the value of the point estimate. So in the first one, the makers of a new golf ball want to estimate the median distance the new balls will travel when hit by a mechanical driver. They select a random sample of 10 balls, you see that word random, and measure the distance each ball travels after being hit by the mechanical driver. And here are their results in yards. And so they list them. So in other words, they want to estimate the median distance of all the new balls when hit by a mechanical driver. And in this case, here are the distances that were hit after 10 random sample of balls were selected. So what should we use in this case? So write it down. Right now, write down what you think it is. We'll cross it out if it's wrong and fix it when I go over the answers. So if I want to estimate the population median, what is my best guess? What should I find? And then find it. In part B, the golf ball manufacturer will also like to investigate the variability, the spread of the distance traveled by the golf balls by estimating the interquartile range. So they would love to know what the true interquartile range is of it, but they want to estimate that true. So what are we going to use to estimate the true interquartile range? What is our best guess of the true interquartile range? And then the last one, the math department wants to know what proportion of students own a graphing calculator. So they took a random, look at that random again, isn't that interesting? Sample of 100 students and found that 87 own a graphing calculator. So we want to know, the math department, we want to know the true proportion. All students, how many of them own their own graphic calculator? What percent of them own their own graphic calculator in the high school? I don't know. But you know what I'm going to do? I'm going to collect a random sample of 100. What should I use to estimate the true proportion P? So like I said, hopefully you're writing down your answers on this. And you could see what we're trying to go through is if I'm trying to estimate the true median, if I'm trying to estimate the true interquartile range, if I'm trying to estimate the true proportion, what I'm going to use is I'm going to use the samples of those. So the sample median is the best guess, the point estimator for the true median. And if I were to list them off on there, the sample median there is 285 yards. The sample IQR is the point estimator, the best estimator for the true IQR. So I would find with the interquartile range of this, and it would be 3. Maybe you want to make a note here, interquartile range is not the interval 284 to 287. It's a number. You remember that from way back in previous chapters. Use the proportion. If I want to find the true proportion, estimate the true proportion, I'm going to use the sample proportion, p hat. And if I found 87 from my random sample of 100, I would say the p hat is 0.87. So this is meant to show you the point estimator for an unknown parameter is the statistic of that one. let's put this into practice, kind of just doing a little activity together since we're not in the classroom with this, is the idea of confidence intervals. We're going to figure out what is a confidence interval. We're going to use semester exam grades. Now, don't worry. These are semester exam grades. No names are put on these, so you're okay. So what we have here is we are going to take our best guess at the mean of the semester exam score. So think about that. Based off what we just did on the previous slide, if I want to guess the true mean of the semester exam scores, what am I going to use as my point estimator? Don't worry, it's also with points back, so we're okay. We're going to create a confidence interval, and so maybe underline this because this is the part that we're doing that's new. A confidence interval is your point estimate, your best guess, plus or minus a margin of error. And we're going to figure out what that margin of error is as we go through the lesson. And the person who creates a confidence interval with the smallest margin of error that still captures the true mean will win a prize. My respect for you. So in this case, let's do this. I have, if we were to take a look at it, I have a list of the exam scores. Again, I have an ID. And if I were to look at this, it looks like there are 139 students who took the semester exam. That is our population. And so that's a population, and we know what I'm going to do is I'm going to kind of talk through some of the conditions that we've dealt with before. That's my population, and I'm going to write that down, is that I have, in this case, I'll put it right here, n equals 139, so I have a number that's attached to it. And I'll write down a little bit later, that represents all the New Albany High School students who took the semester exam. Now, how many should I collect for my sample? So I have that list of 139. How many should I collect for my sample? And this is where our conditions from before come into play. If I need to collect a sample and I'm doing it without replacement, with replacement, without replacement, in this case I'm doing it without replacement. I'm going to grab, and I'm not going to put it back because I don't want to see that same person's score. So I'm really doing this without replacement. So I need to check independence. And if I'm checking independence, that means I need my 10% condition. 10 times my sample size must be smaller than my population. So if my population is 139, then n has to be less than or equal to 13.9. The largest sample size I can collect is 13. That is the largest sample size I can collect without violating independence. So we have that. That's good news. Now, the problem is this. What about normal approximation? Normal approximation says that if you have a sample size that is small, that is less than 30, you need to hopefully have selected it from a population distribution that is normal. Because if the population distribution is normal, the sampling distribution is going to be normal. And my sample size is less than 13. And you know, the odds are, it's amazing, this population distribution just happens to be normal. I mean, who knew? But in the grand scheme, we do always need to check that as well. So I'm telling you, don't worry, the population distribution is normal for the exam scores. So I didn't violate that condition, don't worry. And so what I did is I used in my calculator down below, I went to math, probability, and I selected random integer no repeats, and I went through and I did it for 13. And so here is my information for my sample size of 13 and the scores. And so I have my scores. I found the sample mean, so I found X bar. It's 86.4%. That is my point estimator. It's my point estimate. It's my best guess for the true mean. My population is going to be all 2019, 2020 students who took this exam. And that would be 139, n equals 139. My sample was a random sample of 13 AP Statistics students. My parameter, my mu, I don't know. We don't know. It didn't tell us there. But my statistic is X bar, which is 86.4. Now, we are going to change our point estimate. So my point estimate is 86.4. And what we want to do is we want to add and subtract the same number from that point estimate. And we get to choose that number for right now. Right now, we are choosing. That's not what we do for statistics, but we're trying to show you. That number we're going to call that's being added and subtracted from it, that is going to be called your margin of error. And so I'm just going to pick one. I'm going to pick, I want to capture the true mean somewhere in that interval. So right now I'm saying 86%. Well, 86.4 if we want to be specific. I'm saying 86.4, that's my best guess right now, but I'm allowing myself some wiggle room. So what do I want it to be? You know what? I think one of the students got 100%. I do. But that's not, that's not the mean. I'm gonna probably, let me do 14. No, I can't do that. Let me do 13. So I'm gonna do 13. So if I add 13, I'm going to have, for this, a 99.4%. I really trust in your average. I think it's a 99.4 is the highest that you can go for the average. And if I go down to the other side and I subtract 13, it's going to be a 73.4%. Now, I chose that because I think you guys might have done really well in the exam, and maybe the average is in the A range. And I want to make sure it's in the A range, but maybe there are a couple students I wasn't so sure about. Maybe that outliers took it down to the C range. I don't know. So I'm capturing C range to A range on that one. So that's why I chose that margin of error, is I wanted to capture in those. So there's that one, 73.4% to 99.4%. Now, in other words, how big is my net? My net in this case that I'm using to try and capture it is 26 percentage points, because I went 13 one direction, 13 the other direction. So I have 26 percentage points that is captured. My net, my margin of error is 13%. I went 13 above and 13 below. So let's look at the next one. Now this one I forgot to write down the numbers. Sorry, but I did select 13. Same idea. This time I calculated the x-bar to be 88.5%. That's again my point estimator. Same information as before, but now I'm going to do the same idea. I'm going to choose a margin of error on it. And so I have my 88.5%. And remember, this game is the person who captures the true mean with the smallest margin of error. Well, last time I did 13, I'm going to try and capture it. I'm going to be risky here. I'm going to do 5%. I'm going to go 5% above, and I'm going to go 5% below. So that would be 83.5%, and this would be 93.5%. So that's a smaller net. I had a smaller margin of error, so you can tell how that's only 10 units from interval to interval. That's a smaller net there. I could even do it if I selected 5. Then I went through and did 5, and in that case, I got 89. So maybe I think 89 is too high. And if 89 is too high, I want to make sure I have a margin of error that goes down below what it is. But let's just kind of go to the rest of them. Based on my answers in 1 through 3, write an interval that you think contains the true mean. So I had 2 of them. I had 83.5, 93.5, and I had this one. So I'm going to write down both. Boom. And then I had 83.5 to 93.5. Those are my 2. So if I'm looking at this, one of them has a net that was 26 from interval to interval, a margin of error of 13. One of them had a margin of error of 5, a net of 10. How confident do I feel? I'm pretty confident it's between a C and a 99.4. I mean, think about that. If I throw a large net, I'm pretty confident I'm going to capture something. You know what? I'm going to say I am about 98% confident that I'm going to get something there for the average, because that's a pretty large net. I'm bound, if I throw a large net, to capture it. But however, 83.5 to 93.5, I mean, that's a smaller net that I'm throwing there. I'm not sure I'm going to capture. I'm only giving myself a 10 percentage point chance of capturing. Yeah, I don't like that. So maybe I'm only about 90% confident here because my net's smaller. So one group said 71 and 79 is their interval. They think the mean falls in there. What's their point estimate? So if someone comes up to you and says, hey, my interval is 71 to 79, so 71 is their lower part of the net. 79 is their upper part of the net. How can you figure out their point estimate? Well, the point estimate takes the middle and you go the margin of error to the right and you go the margin of error to the left. So really it's going to be the midpoint in that case. And if I think about the midpoint here is a 75%. So I'm going to say their point estimate was a 75%. Their margin of error then was a 4% because 75 plus 4 is 79, 75 minus 4 is 71. In another group, they claimed the true mean exam score is at 84%. Does our interval support that claim? So in other words, our intervals are right here. Do those intervals support the claim here? And in this case, yes. Why? Why do these two intervals support the claim that 84 is the true mean of the exam scores? Well, if I look at that, did this interval right here, if I were to find 84, is 84 somewhere in that interval? Yes, it is. I mean, is 84 somewhere in this interval? I got close there. It is. 83.5. Man, I barely captured that one when I threw that net. But it is. Both of these do. Now, here's the true one. The true mean was at 87.8%. Did we capture the interval? Both people managed to capture the interval because 87.8 falls in both of those intervals. And if so, what was your margin of error? We figured out this case, if 87.8 was, what's interesting here is this. Who captured it? Well, they both did. One of them had a smaller margin of error. One of them's margin of error was 5%, 83.5 to 93.5, but one of them had a larger margin of error. They were more likely to capture it because they allowed 13 percentage points left and right. The 83.5 to 93.5 was less likely to capture it in a way because it was so much smaller. So it's an interesting thing with this. This is meant to kind of show you. We just did this, like, what did we really learn? Well, we learned if I know my interval, I can find the point estimate and I can find the margin of error. And we're starting to figure out, that net size. What's the point? What's a good one? So here's our big ideas of what we just did. The big idea is that sampling distributions of x bar tells us how close to mu the sample mean x bar is likely to be. All confidence intervals that we construct follow this form. Your point estimate, your best guess, plus or minus a margin of error. So a confidence interval for a parameter has two parts. It has an interval calculated from the data, estimate plus or minus the margin of error. And the margin of error tells us how close the estimate tends to be to the unknown parameter. Notice, right here, remember, these are the things that kind of pop up a lot in multiple choice. It tells us how close the estimate tends to be to the unknown parameter in repeated random samples. A confidence level is the second part. That's the overall success rate of the method for calculating the confidence interval. That is, in other words, C% of all possible samples of that same size, the method would yield an interval that captures the true parameter value. So we usually choose a confidence level that is 90% or higher. The most common, highlight it, underline it, but the most common one that we use is a 95%. So if you're not told what level to use for a confidence level, use 95%. That's the most common one that we do. Now, one thing before we move on to the next slide to keep in mind is this. Confidence level, and I know this is written 1 then 2, but however, confidence level can be found and interpreted at the beginning of the problem. Before you start a problem, you state your confidence level. How confident are you that you're going to capture the population mean in repeated samples? So confidence level can be told right away. Confidence interval has to wait to the very end of the problem. You can't tell me the confidence interval until you do the work. So, confidence level, you can do right in the beginning. Confidence interval at the end. So is it good to be really confident in a way? To be 100% confident? If I'm 100% confident that I am going to capture the true population, that might sound like a good thing. But really what that means is I am using a large margin of error. I threw out a net so big, I guarantee I'm going to catch something. There's no way I'm going to miss because the net is so much bigger that it needs to be that when I throw it, it's going to capture it. And that's what this cartoon is meant to show you. If the weatherman's on there and say, hey, tomorrow's temperature is going to be between 40 degrees below zero and 200 degrees above zero, I mean, that weatherman's 100% confident he got it right. He's going to capture the true temperature tomorrow because he threw out such a wide net, it's going to capture it. And he's never going to be wrong if he always does the weather that way. So that's the idea, is sometimes too much confidence is not a good thing. So keep that in mind when you're thinking about the interval. So right now, confidence intervals, we said it's your estimate plus or minus your margin of error. Now what the margin of error is, and we're going to get to this, is the margin of error consists of a critical value for Z or T. We're getting there, don't worry, times your standard error. And so the main idea is there is a way to calculate your margin of error. We can take our critical value times the standard error, and that's what equals your margin of error. So your margin of error equals your critical value times your standard error. That's what we're going towards. There's a way to calculate it to make sure that we can do it right. And these are the formulas in Chapter 8 that we're going to be looking at. And so notice the structure is the same. You don't know these yet, but the structure is the same. X bar, that looks like a statistic. P hat, that looks like a statistic. X bar again looks like a statistic. That's your point estimate. Plus or minus, plus or minus, plus or minus. And so we could see the different parts. And I'll make it so we can actually do this. Here's our critical value, Z or T, right here, right here, right here. Here is our standard error formulas. Well, I need a better color than that. Here is our standard error formulas. Here, here, and here. And notice it says Z star, Z star, T star. So those are going to be coming to play on, those are critical value notations. And so we continue on, and we're going to be doing this repeatedly when we start doing two samples, the same thing. And when we do Chapter 12, it's going to be the same thing. So we start to see things go in. Now, what I'm going to do is I'm going to pull up an applet right now that goes through and shows you what confidence levels and intervals really are. All right, so here we go. This is something to kind of simulate what is a confidence level. And so right now, I'm setting our confidence level at 95%. And what this is going to do is I'm going to hit resume, and it's going to start capturing. And right now, my sample size is 5. And so when my sample size is 5, take a look at some of these. Now what this is each one of these, so each segment represents one confidence interval. So you can see right there, you see a lot of them in this case, and I'm really pointing towards the one that is right below the red here. That's a confidence interval. That blue dot is your point estimate. The distance to the right is your margin of error. The endpoints in that segment, those create your confidence interval. And what happens is it's collecting many of these. And we're going to kind of see that's really what we're looking at for a confidence level. And so far right now, because I quickly tried to pause it, you can see on the top here, it says your confidence interval coverage. So far, it collected 51. As soon as I went to the page, it just starts. So it went through and it did 51 samples. It missed 3 times. So if I look over here on this right-hand side, notice there are 3 red segments there. And they do not overlap with that dashed line. That dashed line is the true population mean. So it missed it. All the other ones, the black ones, you could see overlap on that population mean. And so it captures that population mean. And what a confidence level is so far out of the 51, I captured it 48 times. So in other words, I collected and constructed 48 confidence intervals that captured the true population mean. However, I constructed 3 confidence intervals that missed. So I threw 51 nets into the population, and I captured the true mean 48 times. I missed 3 times. So if I hit resume, it's going to keep going, and it's going to be collecting and going, and it's going through, and you can watch what's happening. So far, you can see I'm collecting. Right there, I missed. You see that red segment? I missed there. It did not capture it. And what you can do is you can see, as we're going through in the middle here, you can see that it's starting to calculate what percent is actually capturing. And we wanted 95. And so though I don't see what's going on, you can see it going back and forth, back and forth. Now I'm going to speed this up for us. And it's going to keep going faster and faster and faster and faster. So I'm going to speed it up and take a look. It does go a little bit down, and it's going to go through. And the idea is if I were to do this repeatedly, I should get closer and closer and closer and closer and closer to 95%. Now, one thing I'm going to do, and it's going to change it a little bit, is I'm going to increase my sample size. And I'm going to do, let's do 30 just for some fun. And notice what's happening, by the way. What happened here is I increased my sample size. Those segments, those intervals became smaller. Didn't they? So in other words, didn't I decrease a little bit of my margin of error when I increased my sample size? Now that's really interesting. And you can see we start to go through and capture more and more. And so what happens if I increase it more? And you can see what happens. So let's say I do a sample size of 50. Again, notice that also became smaller. What happens if I do this? If I go between them and I go back down a little bit, and if I keep going down, that sample size should make it so the segments, and I'll do get close to 15 here, it gets bigger. So that's something to kind of play around with, is what happens. And you can see we start to get closer. And really the idea here is this. If we go back to the notes and we look at what a confidence interval is and what a confidence level is, there is a difference. As I did say, you could say one before the other. In the beginning, I could tell you what a confidence level is. It is the overall success rate of the method for calculating the confidence interval. C% of all possible samples, all those segments that it was generating there, C% of those should capture the true parameter value. And so let's go through and look more at the information of this. So that was meant to kind of show you. So here we go. And a confidence level is the overall, and this is a really good phrase to know, it is the overall capture rate if the method is used many times. So you start with the population, and imagine taking 16 different simple random samples. The sample mean will vary from each sample, and we can see that here. So I have a population. The sample mean varies. I plot those, and that's this part right here down below. So I plot all those, and I did 16. So notice below, and this is my population. I have my sampling population up here. I have my sampling distribution of X bars, chapter 7. And what happens is I am looking at this, and I can see I missed one time there. That interval missed the true population mean. All the others captured. So there were 16. I captured it 15 out of 16 times. What a confidence level is, and like I said, this is what you need to realize first. That can be done at the beginning of this. So a confidence level says that we are 95%, because that's the confidence level that's stated in the problem. We are 95% confident. All possible samples of that given size from the population will result in an interval that captures the unknown parameter. That's why you can do it in the beginning. I know in the beginning, my sample size, I'm 95% confident. All possible samples of size 16 from the population will result in an interval that captures the true population mean in this case. So right there, that's something to write down on your notes packet in the little boxes there, your little cheat sheet stuff, how to interpret a confidence level. And by the way, you only interpret a confidence level when you are asked to interpret a confidence level. However, a confidence interval must always be interpreted. And the confidence interval is done at the end. So this can be done at the beginning of the problem. This is done at the end of the problem after you calculate it. See, we are 95% confident that the interval from blank lower bound to blank upper bound captures the actual value of the population parameter in context. What are we dealing with here? So here's what confidence level is. You are generating many samples. And you are 95% confident of all those samples that you generate of that sample size, it will capture the true population parameter. It will result in an interval that captures the true population parameter. So 95% of all possible samples of a given size from that population will result in an interval, because that's what we're constructing, that captures an unknown parameter. The confidence interval says we are 95% confident that the interval we find from lower bound to upper bound captures the true population parameter in context. Some common errors that occur. Most students, they confuse interpreting confidence levels with confidence intervals. So, again, confidence levels can be done at the beginning of the problem. If you were to do this many times, what's going to happen? Confidence intervals are done at the end of the problem, after you find the interval. Every time a student constructs a confidence interval, you have to interpret it. So you are always expected to interpret a confidence interval because you are constructing that every time. The only time you ever interpret a confidence level is when they ask you to. Meaning to let you know that a good interpretation of a confidence level will not include endpoints, but a good interpretation of a confidence interval does. Confidence levels do not include endpoints because that's done at the beginning of the problem. So, in other words, you can interpret your confidence level before the data is obtained. You state your level of confidence that you're going to use at the beginning, and then you perform it. You find everything. You find your point estimate. You get your margin of error. You construct your interval, and at the end, you can interpret that confidence interval. So, confidence level tells us how likely it is that our method we are using is going to produce an interval that captures the population parameter if we use it many times. The confidence level does not tell us the chance. Confidence level does not equal chance that our particular confidence interval captures the population parameter. So, confidence level does not equal chance. Confidence level does not equal chance. Instead, the confidence interval gives us a set of plausible values for the parameter. Not possible, plausible. We interpret confidence intervals in much the same way, whether we're estimating a mean or proportion or any other parameter. So population mean and population proportion, we do interpret confidence levels and confidence intervals the same way no matter which one we are finding. So a little bit of exam tip, you may be asked to interpret the confidence interval, the confidence level, or both. So you have to understand the difference between them. So you can take a look there and see that. If you look at this, we have examples of this. According to a Gallup poll in 2010, the 95% confidence interval for the true proportion of Americans who approved the job President Barack Obama was doing, 0.44 plus or minus 0.03, and we can go through and figure out these. Part A says to interpret the confidence interval. So part A, when it says here 95% confidence for our interval, we are 95% confident the interval from 0.41, because I subtract my margin of error, to 0.47 captures the true proportion, the population proportion of Americans who approve of the job President Barack Obama was doing as president at the time of the poll. Now, if I want to interpret the confidence level, in 95% of all possible samples of the same size, it didn't tell me the sample size there, so I'm going to say just of the same size, the resulting confidence intervals would capture the true proportion of Americans who approved the job President Barack Obama was doing as president. True or false, the interval 0.41 to 0.47 has a 95% chance of capturing the true population parameter. No. That's false. Confidence level does not equal chance. Your percent confident does not equal chance. We do not have a 95% chance of containing the actual value. We are in 95% of all possible samples of the same size. The resulting confidence interval would capture the true proportion. That's what that's telling us, the confidence level. We're 95% confident that interval could capture the true proportion of Americans. There is not a 95% chance. The percent chance, by the way, if you want to know, here's the percent chance that the interval from 0.41 to 0.47 will capture the true population proportion. It's either 0 or 1. Because it either captures it, boom, or it doesn't capture it. It either is going to capture it, 1, or it doesn't capture it, 0. And I know this is a blue slide, but if I were a student, I would so pause and kind of write these down as examples for interpreting, because I really like these A, B, and C's foreshadowing. So here we go. Interpreting confidence levels and with confidence intervals. So if I have, in 2013, a survey by careerbuilder.com, we found that 47% of college grads did not find a job that was related to their career major. The study had a margin of error of 2% based on a 90% confidence interval in a sample of 2,134 workers. It yields a confidence interval of 0.47 plus or minus 0.02. Interpret the confidence interval. We are 90% confident that the interval from 0.45 to 0.49 captures the true population proportion of college grads who did not find a job that was related to their career major. Notice the highlighted parts. That's important. However, there's one part that's not highlighted because it would have taken a lot of time for you to write right here. That is your context. And a good expected confidence interval interpretation is going to contain context. Interpret the confidence level. Well, I could have done that in the beginning. So in 90% of all possible samples of the same size, the resulting confidence interval would capture the true population proportion of college grads who did not find a job that was related to their career major. Again, look at the highlighted parts. And again, one part that is not highlighted is right here, and that is context. Remember, you always have to interpret confidence interval. Confidence level is when you are asked. So make sure you can tell the difference between those two. True or false, the interval from 0.45 to 0.49 has a 90% chance. No, false. It either has a 0 or a 1. That is the probability that it will capture. It's either going to miss or you're going to get it. So those are an example. You can pause it and kind of go through it. Again, I would kind of make sure I have an example of interpreting interval and interpreting level on my formula sheet. So pause this, read this. It's one of your check your understandings in the book. It does interpret a confidence interval. It does interpret a confidence level. And it asks you to determine a true or false. So pause. Kidding. You didn't pause. I paused. And now I'll erase. We are 95% confident that the interval from 2.84 to 7.55 captures the true standard deviation of fat content with Brand X hot dogs, and 95% of all samples of the same size of 10 Brand X hot dogs, the resulting confidence interval will capture the true standard deviation. And here, false. The probability is either 1, it contains it, or 0, it doesn't contain it. Wow, that's 3 times we've done stuff like this. So maybe that means I really should have paused the video. Kidding, you didn't pause again. And write these down. So, here we are. Why settle for 95% when estimating a parameter? Why not go for greater confidence? I've already kind of addressed this, and you can kind of go through and read this. When we're calculating a 95% confidence interval for a mean mu, we start with an estimate plus or minus a margin of error. Our estimate comes from a sample statistic x bar, and the sampling distribution of x bar is normal. About 95% of the values of x bar is going to lie within 2 standard deviations. Remember the empirical rule. 68, 95, 99.7. 95% lies within 2 standard deviations of the center. So in this case, our mystery semester exam score, if we were to do this, we would have, if we looked here, you can see a confidence. Now, one thing that's wrong, and I forgot to change this, and I apologize, these should be written in least lower bound to upper bound order. So cross that out and put that in the right order. So it leads to a more general formula. Statistic plus or minus your critical value. So in this case, my critical value, if you want to highlight it, was 2. It lies within 2 standard deviations of the mean. My standard deviation of the statistic was 5 in this case. And so what happens is this right here, critical value times standard deviation of the statistic, is my margin of error. So our critical value, that Z star that we saw, that T star that we saw, is 2. And we get that because it's 2 standard deviations. Now the value of that statistic, the value of that standard deviation was 5. So I went Think about that. From the center, if I go two standard deviations one direction, I'm going to take 2, multiply by 5, bam, bam. I'm going to go 2 standard deviations the other direction, so I'm going to multiply 5 by 2, bam, bam. So that's what that's really doing, is constructing there. It relates to our empirical rule. So, calculating confidence interval. We are going to take our statistic plus or minus our critical value times our standard deviation of the statistic. And again, this is our margin of error. Couple things to keep in mind. Properties of confidence intervals is the margin of error is your critical value times your standard deviation of the statistic. I've said that 3 times. The user chooses the confidence level and the margin of error that follows. So you get to choose. If you have to choose, 95% is the one that you want to choose. The critical value depends on the confidence level and the sampling distribution of the statistic. Greater confidence requires a larger critical value. And think about that. Great. To be confident you're going to capture it, you really want to make sure you get the entire distribution. So then you're going to be 95% confident. So think when you hear that percent confident, you need to think back to empirical rule. If I say 98% confident, I'm capturing beyond 2 standard deviations there. Standard deviation of the statistic depends on the sample size. We saw that in that applet where we had animating. As I increase the sample size, the intervals decrease. The standard deviation depends on that. So margin of error, so properties of it, it gets smaller when your confidence level decreases and your sample size increases. So margin of error gets smaller when your confidence level decreases and the sample size increases. If I have, and it's a weird thing to think about, is my confidence, if I were to put the middle right here, I am less confident in that 80% interval than I am in that 95%. Why? Because the net is smaller. And if I think about that net, remember this distance right here is margin of error. So as my margin of error gets smaller, notice I have less confidence, 80%. But as my margin of error gets bigger, I have more confidence. That's what that's telling you about confidence level. It's kind of backward. Well, if I'm 95% confident versus 80% confident, my margin of error, no. Margin of error is the distance from your mean. So the larger the distance from your mean, you're more, should be more confident you're going to get it because you're throwing a larger net. And the smaller the net I have, the less confident I am I'm going to capture it. And the sample size increases. So there we have those pieces of information for us. And let's go on to our conditions, the last part. I had actually addressed these in the first part of the video. Random, normal, independent. Those are our conditions. When we are doing a state plan do conclude, when we are doing a state plan do conclude, just so you can know, these are in your plan step. Random. It must be random in order for us to perform inference. So either a random sample or a randomized experiment. Normal for means, it has to either be from a normal population, or if it's not, then n better be greater than or equal to 30 because of the central limit theorem. Proportions, you must expect at least 10 successes and 10 failures for these. And individual observations are independent of each other, but if you're sampling without replacement, like I did with the means problem for the semester exam score, then that 10% condition must be taken care of. Your sample size cannot be larger than 10%, so 10n less than or equal to capital N, your population. That's what we dealt with before. A lot of these conditions we have looked at in Chapter 7. The one that we really didn't focus on in Chapter 7 is the random, but do pay attention, that must be done. And I know that's a lot, but man, I am 95% confident that you will be understanding where we're going ahead with this. Is really make a note of what a lot of things were. Interpreting confidence level done at the beginning of the problem. Write down an example of it. Interpreting confidence intervals done at the end of the problem. Write down an example of it. What are your conditions? Write down what those are. And really, even what's the property of margin of error? And then, what is margin of error? Your critical value times your standard deviation of this statistic. And that's it. That's my alarm.